Okay, so basically, let me share the cable that I can. So as I was telling you, what I wanted to do next was to like in the next few classes, which will continue after the spring break, um, is to discuss how can you define a version of the gradient, the curl, and the divergence on a simplicial complex. So kind of like the goal for the next few classes is to define the gradient, curl, and divergence of a vector field, let's say, on a simplicial complex. Now, the reason for that, just to give you a heads up or a preview of what I want to do is to kind of like use this to kind of like rank preferences. So there's kind of like so the reason for doing this is to address. So the ranking problem, in the sense, is what it means, or where like you have like a collection of items that could, it could be movies, for example. So you could have like, well, let's just call them objects. So you have like a set of objects to be ranked. So again, like they could be just like movies, for example, movies. And then you will have like like movies are ranked by what you could call agents or users, right? So they will be ranked. So the main issue with like ranking, well, what are some issues with ranking? Well, the first one, that happens in many of the actual ranking problems, maybe it's warm outside, but maybe I should try to close this because I don't want to go to I think it's having better. Right. The main issue with ranking problems, which is similar, which is, you could think about it like with Netflix, for example, is that, in principle, there could be a gigantic amount of items that could potentially be ranked, right? And most agents will not rank all of them, right? So like the data set of like possible rankings, most users or agents will not rank every single item, right? So most users, in fact, will rank a very small subset of all the possible items, right? Will rank a small subset of all the possible items, right? Like example, movies on Netflix, right? uh, like at most, like even if you were a person who ranks every single movie that you see, realistically, you probably don't see more like 20 or 30 movies a year, right? Like that is like a fraction of like all the possible movies, like, that you could see on Netflix. So like any particular user, from them, like you would have like very incomplete data, right? So it's like there's so, usually this data will be very incomplete. That's okay. That's kind of like more like a practical point. The other one is a little bit more philosophical and more like present, which is also related. That happens in social choice theory or like with voting theory, which is like rankings may not be fully consistent, as in like like in the sense like you may not think of preferences being as transitive. So um This is something related to a paradox called Condorcet's paradox, which Condorcet was a French. I don't know if he was a mathematician, or at least like a French thinker, like from I guess 19th century must have been Condorcet's. And that is just again like the and by consistent I mean that the like transitivity may fail among preferences. Um, and like the example, I think I may have even mentioned this at the beginning of the course. You could think about it as like movies, like that someone may prefer the movie A is preferred than movie B, the greater than I just going to use it as preference, right? Like so, someone prefers movie A to movie B, right? And someone prefers movie B to movie C, but for whatever reason, like like movie C is preferred over movie A, but movie C is preferred over movie A, which by itself, and it is, it's not like a contradiction per se, like you're not contradicting yourself if your preferences operate that way, but it is somewhat like, uh, not so nice from a mathematical point of view, right? Because if, for example, you approach like these rankings from a like economics perspective, or like where like economists like talk about utility functions or things like that. If you think of when you have a preference, like maybe you are secretly assigning a value, right? If you're assigning a value to that preference, like you could think about it kind of like in terms of money. Like if you prefer movie A over movie B, that means that you're willing to pay more money to watch movie A over movie B. That's kind of like a very practical way to maybe make this more concrete. So it's kind of like saying that, like if you thought about it, in terms of money, it would be saying like movie A is worth more money than movie B, and then movie B is worth more money than movie C, but somehow movie C is worth more money than movie A. So obviously that cannot be quite correct. So that means that when you have like all these inconsistencies, you cannot really, represent preferences so easily just by real numbers, right? Because on the number line, you cannot like have this type of phenomena. That's not how greater than works, right? So kind of like whenever you have, again, you have like these inconsistencies in quotes because so whenever these inconsistencies are present, that what that reflects is that somehow like the preferences cannot be modeled just like using like real numbers. I think it's just kind of, let me see. Oh my God, this is so noisy. you know. Anyways, I also have like a class that I have to proctor in Livingston after this one, so I'll probably finish a couple minutes before the usual time. But well, all that I'm saying is that um, you know, typically when you have like these ranking problems, you run into these issues, and we want to kind of like understand in a mathematical way, like a useful way to model like the preferences of the rankings. So what will happen, just to again, like I'll go into more details like about this like next time. But in the ideal world, in the ideal world would be where like there's like a consistent global ranking. That's how you would think about the ideal world. So I mean, it's always nice to talk about the best possible situation. So the ideal world is the best case scenario, let's say, scenario is that it would be one where there is a consistent and global ranking. Meaning that, like, again, if you think about it in the movie situation that I was saying with Netflix, that somehow you can aggregate the preferences of all the users, at least of whoever, like all that was able to submit the data, and you somehow weight those preferences, right? In a way that you get a consistent ranking where, like, you can say, oh, movie one is preferred over movie two, and movie two is preferred over movie three, which is more or less like, if you look at the Rotten Tomatoes rankings, mean, that is like a way of, like, that is like an attempt of what they try to do there, because like when you look at those rankings, it is just like a number, right? So like presumably what it's suggesting is that if something is ranked at 90%, it is preferable over like an 85% ranking, right? So if you had like a consistent global ranking, what you would have is like, again, if you think about um the different items that you can rank as kind of like dots. Um, let's say that there are like n items that we're ranking. Oops, sorry about that. So in this situation, in the case that it's consistent, then like kind of like you kind of like rearrange the items, right? So the kind of like the most preferred one maybe would be the first one, right? So this is the most preferred one. And the last one, again, would be the least preferred. And you could even think that in this case, you can kind of like assign a value to each item that kind of like reflects how much it is preferred. Like it's kind of like it's rating, So you would have a function, you know, you would have a function that gives you the value or like the rating of that item. So this would be, you could assign, and then you can assign, and there would be a function f that assigns a value, which again, I'm thinking kind of like as a rating or like a score number, to each item. So again, like the first item would be would have a value f of b1. The second item would have a value f of b2. The third item a value f of b3. The last one would have a value f of bn. And if this is all again like consistent and there are no kind of like issues with transitivity and all that stuff, then it is really like linearly ordered in the sense that you know like the value assigned to the most preferred item is at least greater or equal to the value assigned to the second item, which is greater or equal to the value assigned to the third item in the ranking and so on. But again, like so in the kind of like the ideal case, what I'm trying to suggest is that there will be kind of like this function v, sorry, not function v, function f that gives you the score or like the ranking of the items. So in the ideal case, there will be this function f that rates the items. But what we'll talk about again this next time is that in general, what happens is that what we would do in the general situation is kind of like define an analog. What we will define is kind of like more like an analog of a vector field on a simplicial complex, and this will only occur when the vector field is conservative. Because when the vector field is conservative, if you remember from Calc 3, you have a potential function. So this function f is going to be kind of like a potential function for the vector field. So what we will do next time is that we will construct a simplicial complex based on these items. So that's why I have been calling the set B, because B has been the name that I have been using for the vertices. So the items to be ranked are kind of like going to be the vertices of the simplicial complex. So the items do you want to rank will be the vertices of the simplicial complex. And on the simplicial complex, we will define something kind of like analogous to a vector field. And then on the simplicial complex, kind of like a discrete version of a vector field. And what will happen is that once you have a version of the vector field, again, we'll have kind of like a version of a vector field. So once you have a vector field, you can find we will have kind of like a version of the curl of the vector field, and together with the curl of the vector field. So again, just to remind you, what was the curl of a vector field? The curl of a vector field, and I'll actually talk a little bit more about this in a moment. Like in Calc 3, the curl of the vector field was something like this, right? Like what you would write as nabla cross F, where F was kind of like the force or whatever. And what would happen in Calc 3 is that, when the curl vanishes, right, that you could then try to find like a potential function, right? So when this vanished in Calc 3, when the curl vanished, we would find a potential function for the vector field. And the idea is that something similar will occur in this situation, but the analog of then what the potential function would do for our problem would become like provide a global ranking to the problem. So in our situation, there will be, when our discrete curl vanishes, well, there will be an analog of a potential function which provides like this ranking of the items. But we will also measure how close we are of finding this potential function, and that will be some sort of like least squares problem, basically. But since this potential function may not exist in general, we will also measure how far away we are from this ideal situation. So it's kind of like I like this example because it's kind of like a nice application of multivariable calculus to a problem that you may not have thought about it, that you can use kind of like ideas of calculus to rank things, you know. I think, and also it's like a good excuse to kind of like go over like some notions of calculus, but from a more general perspective, so that you see how to implement it in different contexts. Um, so again, that's kind of where we're headed. But as I was telling you last week, The main issue, even to implement all of this strategy, the main issue is actually with the definition of the curl that you are given in Calc 3. So the definition of the curl that you have from Calc 3 is not ideal for our purposes. So let me also now start to the nitty-gritty of what we're going to do today. So the main issue to implement this is the fact that the curl of a vector field is not defined in the best possible way in Calc 3. And now what I'm going to do is explain why that is the case. Okay, so just to kind of like remind you what was the formula for the curl. Um, the curl in Calc 3, one way to write it down as a memorization skill. That's actually why this notation is used, because it's supposed to remind you of how you would find the cross product between vectors, right? If you remember in Calc 3, there was this trick to find the cross product in terms of like a determinant of a 3 by 3 matrix, right? And if you remember how the determinant works, it's plus I minus j plus k. And each of these unit vectors, right? By the way, okay, actually, instead of, well, I'll keep them as ijk, but I'll write them as e1, e2, e3 next time. So each of the unit vectors, ijk, it gets multiplied by the determinant of a 2 by 2 matrix, right? So for example, the first one, the one with I gets multiplied by the determinant of the matrix that you get by deleting the row and columns that I belongs to. So it would be this determinant of this 2 by 2 matrix. But how do you do the determinant in this case? So the way, again, like the way to interpret the multiplication in this context was just to do like the corresponding partial derivative, right? So you would take the partial derivative of the third entry of the vector field with respect to y. And then minus, because if you remember, like a determinant had a minus, then you would get. And then the next one, you would delete the row and column that J belongs to. And then you would do the determinant that well, I was trying to show you there. And the last one would be this formula. Okay, so that was the formula for the curl of a vector field in Calc 3. Is that okay? Is that making sense? Okay, but what I'm claiming is that the main issue that this formula has is that it kind of like is based on the formula for the cross product. It kind of like follows the structure of the formula for the cross product. And the problem with the cross product, which is what I'm about to tell you now, it's going to be a small rant of why the cross product is not that great. But one of the main issues of the cross product is that it's only defined for vectors that have 3 entries. Okay, so the issue with this formula is that it is structured on the or based on the cross product. But the cross product as an operation is only defined for vectors with 3 entries, okay? So vectors on R3. Vectors on R3. Okay, so even then, like even if you're focused on vectors on R3, the cross product is not so great. So I'll tell you a few reasons what's not super nice about the cross product. Okay, so that's what I'm going to do next. So what I'll do is tell you what's an issue with the cross product and how to fix it. So there's a way to fix all of this, which is called the wedge product between vectors. I'll tell you what it is in a moment. But so how to fix this? Or sorry, before fixing it, what are some issues with the cross product? Well, besides the fact that it only works on R3, besides the fact that it's only defined on R3. Okay, so issue one um, is that it is not associative. So the cross product is not associative. Okay, what does it mean to say that the cross product is not associative? It means that you cannot like that parentheses are needed when you do the cross product. So meaning, so if you have three vectors, u, v, and w, if you have three vectors, and I want to take the cross product of u with v with w, like actually, let me write it this way first. So the thing is that you cannot write this. Like if I ask you to find the cross product of three vectors, you're not allowed to write it this way because this is ambiguous. So this does not make sense unless you put parentheses. So for example, you could mean this, okay? You could mean this, but that is not the same as u cross v cross w. Meaning that, so it's useful to kind of like think about what's happening here, because if you notice, the way I'm writing the vectors is u followed by v followed by w, and this is u followed by v followed by w. So the vectors are in the same order, so I'm not switching the order of the vectors, right? So this has nothing to do with the fact that the u cross v is minus v cross u, right? This is unrelated. This is unreal. Let me write this down. This has nothing to do with the fact that you know, U cross V is not the same as V cross W because there, when you compare here, I am changing the order in which I'm writing the vectors, right? Here I'm writing U, V, and then, sorry, yeah, here I'm writing U and then V, and now I'm writing V and then U, right? So I'm switching the order in which they appear. I'm not switching the order in which they appear. I'm always writing U followed by V followed by W, and this is U followed by V followed by W. So it is a different type of issue. In fact, with matrix multiplication, you don't have this problem. With matrix multiplication, um, matrix multiplication is a good example because matrix multiplication is associative but not commutative. So so a good comparison is matrix multiplication, where A times B is not the same, right? When you have two matrices, A times B is not the same as V times A, right? But it is still the case that A times V times C is the same as A times V times C. So like the parentheses can be moved around when you have matrix multiplication. So again, like when you have cross product, it is an annoying feature, the fact that the parentheses kind of have to always be preserved. That is like a nuisance, and it kind of like indicates to some extent that maybe it's not the best of definitions, because usually uh, when you have multiplications of sorts, like you do want the operation to be associative, so you don't want to worry about parentheses when you're working with them. Um, the other one, the other reason is that, well, maybe I should also, maybe I should put like an example that shows why the parentheses matter, because I'm not sure if everyone saw it in Calc 3. I always mention it when I teach it, but like, not everyone may have seen it before. But so here's like an example that illustrates this, which is I cross J versus I cross J. So again, if you see what I'm writing I, J, right? So I'm really writing the vectors in the same order. The only thing I'm changing is where I'm putting the parentheses. What's the effect of the parentheses? Like, kind of like as in algebra, the parentheses are there to just say which operation you do first. So here, if I got the parentheses here, I'm doing like the cross product of I with J first. So what is I cross J? That was K, if you remember that. So this would be I cross K. Okay, and then what was I cross K? That was negative J, if I'm not mistaken. Okay, so if you do this cross product using the parentheses for the last two factors, you get negative J. But now, what happens if you do the same cross product, but using the parentheses between the first two factors? So you have to do I cross I. Anyone remembers what I cross I is? That should be a bit easier. What was I cross I? It was zero vector, right? Because the cross product of a vector with itself is just zero. So you get zero cross J. And then you can, when you do the cross product with anything, you get this, sorry, when you do the cross product of the zero vector with anything, you always get the zero vector. So you kind of like end up with two different answers, right? You get with this either the zero vector or minus J, depending on where you position the parentheses. Uh, But that doesn't happen with any other multiplications that you have ever studied. That doesn't happen with matrix multiplication. Matrix multiplication does not depend on where you place the parentheses. That also doesn't happen with, multiplication of regular numbers, and so on. So definitely, that is an annoying feature. The other annoying feature is that the cross product is more what people call like a pseudo vector, actually. It's not really a vector, it's a pseudo vector. So I'll tell you a bit about that. So this is issue number 2. Uh, Okay, so which is like maybe not. I don't think you have. If you took a physics class where they talk about angular momentum, they may mention that, but I don't know how good of a job. It's a subtle point, right? Like so, it's tricky. Like this is where like the cross product gets tricky. So not a vector. Physicists call pseudo vectors sometimes like axial vectors. So pseudo vectors. But I'll explain what I means because it's like an important thing to know. Pseudovectors are also known as axial vectors in physics, while like the honest to God vectors are called polar vectors sometimes. That terminology I always found it very confusing, so I always have to check which one is which, but it's just easier vector and pseudo vector to just remember which one it is. But while the regular vectors are known as polar vectors. Okay, so I'll explain to you what's happening here. Let's see. It's like a very cool idea, actually. So I'll put it in a very simple situation. So you can do this in more generality, but this is enough to kind of like get the point across. This is a kind of like, if you ever learn magnetism, it's one of the confusing things when you're learning like the magnetic force, like the Lorentz force, and all those things, because those involve like cross products. So, but it's like a fun idea. So let's say okay, I'll try to draw two pictures here. Okay, let's say that you have a particle moving on a straight line at constant velocity, just to make your life as easy as possible. So let me draw a line. Okay. So then there you have a particle. Okay, and okay, let me see how I want to draw the particle here. So that is like, I'm drawing. When you have the particle, you can draw the position vector of the particle, right? So this is the position of the particle, maybe at some time t1. So the position of the particle, position vector for the particle at time t1. Okay, and if the particle moves in this direction, actually, let me draw the velocity vector a bit more clearly. If the particle is moving in that direction, then at a later time, then the particle would be here, right? So far, so good. Is that making sense? Okay. So when you have, when you have a particle moving with a certain velocity, you can find its angular momentum, and the angular momentum of the particle is just mass times r cross v. So the angular momentum is called L. Right? And this is r cross the linear momentum, or oh, this is okay. So if you remember, I mean, if you remember how to find the cross product from like the picture, you use the right hand rule, right, to find the cross product. So you do R cross V, the idea that you place your right hand along the vector R, right, and then you can like twist your fingers towards the second vector V, and then the angular momentum is perpendicular to thumb, the direction of your thumb. So here, I mean, it's kind of hard to draw it, but I have to draw a vector that's kind of like perpendicular to these two, like right to the red one and the green one, and so it's kind of sort of pointing up in a sense. So let me see if I can. I don't need this here, but okay, you have to have some right, because this is not going to look that perpendicular to this. Am I making my life harder by doing it this way? Yes, possibly, but yeah, I'm just trying. I feel like if I have drawn it, I just wanted to draw it in a way that okay, I'll cheat a little bit. So fun. I just like it's otherwise the picture won't look that great because it's complicated sometimes to draw this. Uh, so now this is going to look a little bit better. Sorry about that. These pictures sometimes are the hard to draw. Let's see. If yeah, because I'm just trying to illustrate the point, so I might as well make my life easier. Um, so again, if this is like the particle at some time, yes, I should make my life the easiest. So now and then this is the particle at a later time. Wait. And this is a velocity vector. Okay, so yeah, now when you do R cross B is now trying to point up, so I'm pointing in the direction of the positive z-axis. That's what I was trying to do. Okay, yeah. Is that when you try to do 3D pictures on the plane or on a piece of paper or like on the screen, it is a little bit trickier. So I'm just trying to find a configuration where this doesn't look that bad. So for example, that's yeah, if I draw them both on the position, the line on the xy plane, it's easier because then the angular momentum points in the direction of the z-axis. Okay, so that is. But again, like you could totally do it in general. It's just like then I would have probably have used GeoGebra, which I should have done, so that it would have been easier to see. So I regret not doing that. But okay, so now what you can do, so again, and this is kind of like the particle at one time, and this is like the position of the particle at a later time, and this is the velocity vector. Um, Okay, so now what you can do is kind of like do what physicists call like a reflection. So a reflection is kind of like similar to what happens when you put a mirror, right? If you had put like if you put a mirror, if you imagine like the board becomes a mirror, then what happens when you put a mirror is like kind of like it changes the value for like um well, if you're facing the mirror, like, if this direction is like the y-axis, then the value of your y-coordinate, like, changes its value from, say, from positive to negative or negative to positive. So you can do like a reflection. So what I'm going to do next is called like a reflection. And what a reflection does is, again, it changes the point x, y, z into the point minus x minus y minus z. So, and you should think about it kind of like similar to like kind of like a mirror image of sorts. So x, y, z changes to negative x, negative y, negative z. So, for example, just to be concrete, let me see, just to be a bit more concrete, it's easier to draw this first on the XY plane. So for like on the XY plane, what is a reflection? On XY plane, the idea is that if you had if you had if you have here x comma y, its mirror image or like its reflection would be minus x comma minus y. So this would be the reflection of x comma y. And in 3 dimensions, again, that one's going to be a bit trickier, but in 3 dimensions, if you had x, y, and z, yeah, this one won't look that great. But if you had x, y, and z, then the idea is that the reflection flips all the values of the coordinates, right? Which is kind of like just like the vector. So basically a reflection changes its vector to its opposite. You just change it, like reverses the direction of the vector. So a direction, so a reflection reverses the direction of the vector. So I'm gonna write it down here. So a reflection, so that the reflected vector points in the opposite direction. Is that okay? Is that making sense? Whew. Okay, so now the kind of like the fun part here is to think of what happens if you reflect. Okay, so let's try to reflect the picture that we had a bit earlier. So now what I'm trying to do is kind of like find the reflection of the current situation. So again, in the current situation, um, so we had a line, right? This line, well, or like a line segment, right? I drew this line segment in the first quadrant, right? So if you look here, right, because it's on the first quadrant, both x and y are positive, right, on the first quadrant. So if I reflect this, right, what that means is I have to change the values for x and y of the points on this line segment, right? So that means that x and y become both negative. So that means I have to draw it on now on the third quadrant, right? Because on the third quadrant, that's where x and y are both negative. So again, it's not super great to draw this on the third quadrant because the third quadrant is kind of like behind the picture in a sense. But just to try to put something that is kind of like decent enough. Again, like you have to imagine that. the y-axis continues this way and that the x-axis continues this. Oh, okay, it doesn't look that bad actually. Okay, so this is kind of like first quadrant, right? And then this is the second quadrant, this is the third quadrant, and this is like the fourth quadrant. So now this is where the line is located at, right? Like the reflection of the line. Um, And then let's keep track of the 2 points that I drew. You do have to have like at least two reference points. So let me see if I can zoom in. Oh yeah, I can zoom in to show you everything. So again, R of T1, right? R of T1 when it gets reflected, uh, of the 2 points, this one was closer to the x-axis. Um, In fact, like the way I drew them, it has like a smaller length than the second one. So this one is closer to the origin if you want, yeah, that's how another way to think about it. So the R of T1, when it gets reflected, should be maybe somewhere in here. Let me see if I can move this a little bit to the top. Well, that's the reflection, like that's actually I should use different colors so that it's a little bit clear which is which. So this is a reflection of the gold vector. And the pink one, I'll just leave it to be the second one. The pink one kind of like looks like this. So again, like in the original image, the gold vector was closer to the origin, right? In the reflected image, the gold vector is still closer to the origin. That's fine. And so that's kind of like how it looks in this way. So what that means, again, we were moving from the T1 to T2, right? So in the reflected image, we're moving from T1 to T2, so now the velocity vector points in this other way, right? So now, and so now that's how the velocity vector points, right? Because again, the particle was moving from position one to position two. Now position one is here and position two is here. So you're going from position one to position two. So now the velocity vector, before it was kind of like pointing, well, how this would be north, right? If you think of the y-axis, positive y-axis as north. So before it was pointing in the northern direction and now it's pointing southwards, which is what you would want because it got reversed. So the point is that the velocity vector gets flipped, right? It actually points in the opposite direction. If you look at it kind of like in this mirror image world. So like the velocity vector gets reversed as well. Okay. So the velocity vector was reversed or reflected if you want. Vector was reflected. Is that okay so far so good? Is that making sense? Any questions up to this point? But what happens with the angular momentum? What happens with the angular momentum? If you do R cross V again, now this is a new R and this is a new V. If you do R cross V, it's still pointing up. So the angular momentum didn't flip. It didn't go opposite of what it was before. So the angular momentum is still pointing up. So in other words, the angular momentum, when you reflect the position and velocity vectors, the angular momentum stays the same. It didn't behave as a position and velocity vectors. It doesn't get reflected. So kind of like that is odd. So the angular momentum didn't change its direction. after being, when it was, when everything, when all the other things were reflected. That's property of the cross product. It is a property of the cross product. Yeah, yeah. In fact, I mean, kind of like a more intuitive way to think about it, if you go back to the mirror analogy, it's like if you kind of like saw yourself, through a mirror, your right hand becomes your left hand, right? So that is messes up everything, like in the how you keep it when you're keeping track of the directions. So but yeah, like, in general, that's why it's called like a pseudo vector, because when you apply a reflection, it just doesn't change in the same way as the position vector and the velocity vector were changed. So it kind of like remains like the same after reflecting everything else. Um, and again, like that is especially confusing in if you like in magnetism, because if you look at the Lorentz force for a magnetic field, it's kind of like V with the velocity vector cross the magnetic field, so it involves a cross product. So it's kind of like you can have like these problems where you have like a wire, and so an electric wire creates like a magnetic field, and then if you have a particle in a magnetic field, there's like a Lorentz force on it. So you can ask how the particle gets deflected by the magnetic field, as seen in the real world versus seen in the mirror world. But then you have to keep track of the fact that the cross product is behaving in a weird way, under reflections. So all of this is just to say that the cross product is like an odd operation, because it has like these features. First, it's only defined in 3 dimensions. Second, it's sensitive to the use of parentheses. And third, it has this like behavior of under reflections, which is not what other vectors behave as. So it has all these like odd characteristics. So the idea is that you actually, no one has like undergraduate courses works with the cross product. You use something that's called the wedge product. So the wedge product is meant to be a fix basically to all these problems, which I'll tell you about today. So the wedge, well, at least at the beginning, we'll continue with it next time. So the wedge product will be defined for vectors with any number of entries. It's associative, and it's very easy to understand what happens when you do the reflection. So it's kind of like the best of everything. But there will be a price to pay, but it's actually a convenient price to pay. Obviously, there had to be a trade-off somewhere. You cannot just improve everything like without for free. So the the fix is to use something which is called the wedge product of vectors. It literally is written as U cross V, so it's written as, which is written as U wedge V, written as U wedge V. So this is a symbol that is used for a wedge product. So this is the symbol of a wedge product. It's kind of like this and from like if you take like propositional calculus, when they talk about the and the or, that's kind of like the symbol notation for like an and of propositions. I mean, like again, like you cannot just have like new symbols for everything, so you just have to repeat them at some point. But this is the symbol for the wedge product. But the nice thing is that, again, the nice thing about this is that these wedge product of vectors can be defined for two vectors in Rn, so it is not exclusive to vectors in R3. So before I tell you how it's computed, so the main features that it has, uh, it is defined for arbitrary vectors for two arbitrary vectors in Rn, meaning that they don't have to have 3 entries, meaning they don't have to be in R3, have to be 3-dimensional. Another thing that will happen is that it is associative. I'll write that again, what that meant. And it is easy to understand how it behaves under reflections. So it is easier to understand how it behaves under reflections. So associative, as I was saying earlier, just means that if you have three vectors, sorry, so what will happen with associativity is that if you have three vectors, you wedge V, wedge W. If you take the wedge product of three vectors, the parentheses won't make a difference in this case now. So U, wedge V, wedge W, it doesn't matter where you place the parentheses. Like you can place them in the first two factors or in the last two factors. So okay, so of course, as I was saying, there is a catch to all, and it's kind of like snake oil, right? Like, you're promising too many good things. So the only catch is that in fact, this is no longer a vector. So the wedge product is not going to produce a vector, right? And when you take for example, when you take the dot product of two vectors, you get a scalar, right? When you take the cross product of two vectors, you get a vector. Now, when you take the wedge product of two vectors, you don't get a vector. You get something that's called a divector. And then what I'll tell you, at least I'll draw the picture of what it is, and then next time I'll tell you more about it. But that's the main catch. So the main catch is that the wedge product of two vectors is no longer a vector, rather it is a divector. A bivector, bi because there are two involved, right? Because you're doing the wedge product of two vectors. For example, here, where there are three involved, right? Like that would be something that you would call like a tri-vector because it involves the wedge product of three vectors. So in fact, what will happen is that maybe just to draw a picture, because as I said, I have to proctor an exam in a bit, so I have to finish off today a bit earlier. But just to kind of like show you pictorially how you should think about the wedge product. So what will happen is that if you have two vectors u and v, if you have the wedge product of two vectors u and v, what you do is draw a parallel. So it's similar to the cross product, right? Because I don't know if you remember this from the cross product, that is magnitude is the area of the parallelogram made of the two vectors. So uh, the difference is that with the cross product, it was a vector perpendicular to the parallelogram. The idea with the wedge product is just to focus on the parallelogram itself. So you don't try to find a vector that's perpendicular to the parallelogram. You just say that the wedge product is the parallelogram itself. So the wedge product is represented as a parallelogram. So U wedge V is going to be the parallelogram that you make. So when you have these two vectors, you can make a parallelogram, and the parallelogram itself is a wedge product, okay? So kind of like the thing itself the parallelogram itself represents the wedge product pictorially. Oops, sorry about that. So the only thing, so the wedge product is represented by a parallelogram. But the only thing is that it has to be oriented, meaning that you have to move along the edges of the parallelogram in a particular order, which is oriented. Meaning that you move along the edges of the parallelogram in a particular way. So for example, and this will be the last thing I draw for today. And then we can kind of like take it from here next time. But it's really fun. Like this is one of the most convenient operations for vectors in all of mathematics. It's one of the best things to learn of how to multiply vectors. Like the wedge product is much superior, like by a mile, like to the cross product. So if you wanted to do U wedge V, kind of like you start at U, you kind of like then connect V this way, then you move it kind of like you move in a loop. Kind of like a circuit, but you kind of like start with the direction of the vector u, and then you just uh, use the vector v, and then kind of lose something like this. But if you wanted to do v wedge u, if you wanted to do it opposite, if you wanted to do v wedge u, then you start with the direction of the vector v, and then you kind of like then you move along the edges in that way. So you see, one is kind of like, I mean, depending on how it's seen, like one is kind of like being traversed counterclockwise and the other one is clockwise. If you kind of like take an aerial view of the parallelograms, maybe I'll do it on GeoGebra so that you can see it better like next time. Um, but so it will still be the case that u wedge v is going to be minus v wedge u because it like the difference is that you kind of like travel along the edges in opposite ways. That's kind of like the idea. But when you do v wedge u, you start first with the direction of of v, and when you do u wedge v, you start first with the direction of u. That's kind of like the idea. But so it will still, but then we would like to say that u wedge v is minus. And the minus sign just going to mean that they are kind of like as that they're being moved, traveled in different opposite ways along the parallelogram. Kind of like in the same way with angles, when you say that an angle is minus 30 degrees, that just means that it's being traveled in a clockwise way. So it's used in a similar way to how you deal with angles. But again, well, let's leave it at this, and then next time I'll tell you all these properties of the wedge product, how this is related to the curl, leave some things in place, and I guess probably after the break, then we'll have everything in place so that we can start talking about this statistical ranking problem that I was mentioning earlier about how to rank preferences using the divergence and the curl and all of that. Okay, but yeah, let's end here so that I can be on time for my exam.